Alright guys, so today we want to talk about the concept of the mole. So to do that, let's first look back at average atomic mass. So we know that average atomic mass is the mass that we find on the periodic table. So for boron, for example, it might be 10.81. We also know that this is a weighted average, so it's the average mass of whatever atom that might be based on the naturally occurring isotopes. So we know that average atomic mass is recorded in something called atomic mass units. Okay? And we have atomic mass units because dealing with atoms and their masses in terms of grams and kilograms isn't really feasible. So we said that 1 AMU was approximately equal to the mass of one proton and the mass of one neutron. We really didn't discuss where that came from though. So the definition of an AMU is 1/12 the mass of one atom of carbon-12. So if we think back to our isotopes practice, we know that carbon by definition has 6 protons, and that carbon-12, because it has a mass of 12, also has 6 neutrons. So this is how scientists define the mass to unit AMU. They just say they have the mass of a carbon-12 atom and they have 1/12 that. So this is useful, and we use this in a lot of isotope calculations. However, it isn't really feasible to discuss doing chemistry and chemical reactions in terms of AMU, atomic mass units, because they are so small. So it turns out that average atomic mass sometimes also goes by another name. We call it the molar mass. Okay? So average atomic mass and molar mass are the exact same number off the periodic table, but whereas average atomic mass has units of AMU, molar mass has units of grams per mole. So we could say that for any atom, its average atomic mass, whatever it might be, is the mass of the average mass of one of the atoms in atomic mass units. But the molar mass would be the same number, and it is the number of grams in 1 mole. So let's ask ourselves, what is a mole? So 1 mole, we can go back to our example of carbon-12. Of carbon-12 is 6.022 times 10 to the 23rd atoms of carbon-12. And that's a constant. So 6.022 times 10 to the 23rd is called Avogadro's number. And that's named after a scientist who is a very ugly man, if you ever want to go and check out his picture on Google sometime. But Avogadro's number is the definition of 1 mole. So if I have 6.022 times 10 to the 23rd carbon atoms, I have 1 mole of carbon atoms. If I have 6.022 times 10 to the 23rd iron atoms, I have 1 mole of iron atoms. It's kind of like the term 1 dozen. If you have 1 dozen donuts, you have 12 donuts. So if you have an Avogadro's number of donuts, you have 1 mole of donuts. So this number is very important, and we use it as a conversion factor. So for the conversion factor, we could write 6.022 times 10 to the 23rd. I could say atoms, or I can just say particles equals 1 mole of particles. And the reason I say particles instead of atoms is I can use Avogadro's number to calculate the number of moles of molecules, the number of moles of protons, whatever the case might be. It does not solely apply to atoms. So let's look at a couple of different atoms here and make sure we're on the same page about what this all means. So let's start off looking at sodium. So Na. So So on the periodic table, the average atomic mass, or the molar mass of sodium, is listed as 22.99. So we can say under the average atomic mass, we can say on average, a single Na sodium atom weighs 22.99 AMU. Okay? So on average, a single sodium atom weighs approximately 22.99 AMU, or atomic mass units. So I could also say in the molar mass column, I could say that 1 mole, or that is 6.022 times 10 to the 23rd atoms of sodium weighs 22.99 grams. So we use the same number here, but we have different uses for that based on what category we're describing up here. So if you look in your notes, there is a proof written out for why we can use the definition of AMU and grams per mole interchangeably. But I'll leave that for you to look at on your own. Primarily, we're going to be concerned with the molar mass, because that tells us, how many, sorry, I had an issue with the camera. So that tells me how many atoms or molecules I have in a mole. So it gives me a way that I can convert from mass to the number of atoms I have. Because the number of atoms I have is what I'm really concerned about. When I do chemical reactions, I want to know how many atoms or molecules I have that are able to react with one another. So we'll describe molar mass quite a bit in this course. So a couple of notes about molar mass. First, the units are grams per mole. Okay? And second, we round to the nearest hundredths. Okay, so that's 2 numbers after the decimal place. So when we record these molar masses from the periodic table, we'll record them with 2 numbers after the decimal place. Okay, so if you look in your notes, there's a couple of examples where it asks you to calculate or find the molar mass for some atoms or molecules. So it's pretty simple to find the molar mass if it is a single atom. So for nitrogen, for example, I could look in the periodic table and I can find the molar mass is 14.01 grams per mole. I could also say the average atomic mass is 14.01 AMU. So then I could say iron, for example. I could say the molar mass for iron is 55.85 grams per mole. If your hundredths place is different than mine, don't be concerned by that. I'm using a periodic table from an old textbook I have at home, so the masses vary slightly on periodic tables for reasons that we discussed in a couple of videos ago about the relative abundances varying from location to location. So it's pretty simple to find the molar mass of a single atom. So to make sure we fully understand what that means, I'm saying if this is the molar mass of nitrogen, that means 1 mole of nitrogen weighs this many grams. Or in other words, I'm saying 6.022 times 10 to the 23rd atoms of nitrogen weighs 14.01 grams. I'm also saying 6.022 times 10 to the 23rd atoms of iron weighs 55.85. So then let's look at if I have some molecules or compounds. So if I have sodium chloride in a Cl. If I want to find the molar mass of sodium chloride, I simply add together the molar masses. So I add together 22.99 grams per mole. And then chlorine has a molar mass of 35.45. Okay. So when I add those two together, remembering my rules for significant digits, because they both have 2 numbers after the decimal here, this would be fairly simple. So you should get 58.44 grams per mole. Sorry, cut off there. So what that's saying is, for every 6.022 times 10 to the 23rd molecules of sodium chloride, they weigh 58.44 grams. So if you have 58.44 grams of sodium chloride, you have an Avogadro's number of sodium chloride molecules there. So let's look at one that's a little bit more complex. Okay, so here I have the molecule magnesium phosphate. Okay, so the same general process here. To find the molar mass, you simply add the molar masses of all the constituent atoms together. The only thing that's tricky here is to make sure you get the correct number for each of the atoms. So just to make sure on the same page, there are 3 magnesium atoms, there are 2 phosphorus atoms, and there are 8 oxygen atoms. So subscripts apply only to the atom which they are attached to, but subscripts outside the parenthesis apply to everything in the parentheses. So the 2 right here would apply to the P and the oxygen there, and you will multiply the 4 and the 2 to get 8 there. So after you do that, just add up the molar mass for 3 magnesiums, 2 phosphoruses, and 8 oxygens. So here, I wrote it on my paper just so you could see what's going on, but we need to develop some speed here because later on in the course, this will be the first step of every single calculation that we do this year. So we want to get to a point where we don't have to write all these numbers down on our paper. We want to be able to just go ahead and type these numbers in our calculator and get the answer. So that's why you have several practice problems in your notes to go through. I know it's not difficult, but you do need to get some practice at it so you're able to type it all in your calculator and get the correct answer without writing anything down. So go ahead and try this one. Okay. So when you got your answer, you should have gotten 262.86 grams per mole. So again, if your answer varies slightly in the thousandths place, that's okay here, or the hundredths place, excuse me, because I'm using an older periodic table, so yours could be slightly different than mine there. So if you didn't get that right, go back and practice with your calculator and make sure you can type these in and get them correctly fairly quickly. So now let's talk about what this number actually means. So we know that this is the molar mass for magnesium phosphate. So we know 1 mole of magnesium phosphate weighs this much. So 1 mole of magnesium phosphate is 6.022 times 10 to the 23rd magnesium phosphate molecules. But there are 3 times that many magnesium atoms. There are 2 times that many phosphorus atoms. There are 8 times that many oxygen atoms. So that's why we wrote the definition for Avogadro's number as number of particles. Because whatever we're describing, whatever the molar mass is, that's what Avogadro's number describes. So there are an Avogadro's number of magnesium phosphate molecules, not necessarily magnesium or phosphorus atoms individually.